Hi guys, welcome to your final lesson from chapter 12. Lesson 12.4 talks about the sums of infinite geometric series. So sums of infinite geometric series. First of all, we talked about a geometric series. We said that that's something where we multiply to get to the next term. An infinite series, we talked about finite series in the last section. The very tail end of the last section we said, look, we're going to stop. We're going to take the summation of I equals 1 up to a certain number. So we stopped. So that was a finite series. In 12.4 now we're going to look at something called an infinite series, where now we're going to go all the way up to infinity. All right? So the first thing we have to define is a partial sum. A partial sum of some S sub n. Remember, S sub n is the summation of the terms in a series. A partial sum is basically a summation of the first n terms of an infinite series. So another way to say a partial sum is the sum of a finite series, because we're just talking about the first n terms. All right? Okay, so to make this make a little bit more sense for you, okay, let's go ahead and let's take a look at a rule here. We've talked about sums of a finite arithmetic series. We talked about sums of a finite geometric series. Now we're going to be talking about the sum of an infinite geometric series. So the rule for that says, look, the sum, and notice we don't go up to an n value because we're not taking the partial sum. We're taking all of it up to infinity. We take the initial value, a sub 1, and we divide it by 1 minus r. Now, provided that r is less than 1. This is really important, because if r is less than 1, then r minus 1, this is going to be giving, 1 minus r is going to give me some actual number that I can continue to calculate. All right? And so if r is greater than 1, then as r goes to infinity, then 1 minus infinity becomes basically negative infinity. So this number is going to get larger and larger and larger. Smaller and smaller and smaller. And so, it's not anything that we can actually calculate. All right? So if this right here, if the growth rate, the r, the common ratio, is bigger than 1, then we say that this thing has no sum. I want you to think about the last two checkpoint problems from the previous lesson. Remember how we got like 67 million or something like that for the first 11 terms? Can you imagine going out to the infinite number of terms? There'd just be no way to measure that. But provided that this rate is something that's less than 1, where we're getting exponential decay, for example, now we would be getting something that we actually can add up all the terms, all right? Because those numbers are staying bounded. They're not escaping to infinity. So we can't add up numbers that escape to infinity. You can add up numbers that stay bounded or stay close to 0, all right? So let's go ahead and let's take a look at finding the sum of a couple infinite geometric series, all right? So we want the summation of 6 times 0.6 to the I minus 1, where we're starting at 1 and going to infinity. So again, this is an infinite geometric series because we're going to infinity. So for part A, we see the growth factor here, my r, my rate, a sub 1 is equal to 6, and my r is 0.6. Since that is less than 1, since 0.6 is less than 1, the absolute value of it rather is less than 1, then this is going to be something we can measure. It becomes a sub 1, which is 6, over 1 minus 0.6. Okay, 6 divided by 1 minus 0.6 comes out to 15. And so that says that we can add up all of these numbers as we go to infinity here. We should be able to add up all of those numbers to infinity, and we're going to eventually add up to the number 15, which seems kind of strange. All right, but if I continually take 60% of the previous number, well, then I'm not getting any bigger. So eventually those numbers will add up to 15. Okay? In the second example, okay, again, it looks like we're subtracting and adding, so it would be an arithmetic series, but that's not what we're doing. We're saying, look, the first term is 1, the second term is 2/3, the third term is 4/9, etc., etc. So negative 2/3 divided by 1 just becomes negative 2/3. We have 4/9 divided by negative 2/3, which really says multiply by 3 over negative 2, and lo and behold, you also get here negative 2/3. Okay? So here's what you need. The rate of growth here, the common ratio is negative 2/3, and again we get that by doing this one minus, or this one divided by this one divided by this, or whatever. So if I multiply 1 by negative 2/3, I get negative 2/3. I multiply negative 2/3 by negative 2/3, I get positive 4/9, and so on and so forth. Okay? Now, since the absolute value of this is less than 1, we actually can calculate this series. We can calculate the total for this series. My initial value, a sub 1 in this case, is 1. And so this becomes 1 over 1 minus a negative 2/3, which becomes plus 2/3. And 1 plus 2/3 is 4/3. 1 divided by 4/3 adds up to 3/5. Okay? All right. And then the last one, again, guys, if you got 0.6 for this, that's okay. Just realize that's 3/5. All right. In the last one, if I go -2 divided by 1, I get -2. If I go -8 divided by 4, I get -2. If I go 4 divided by -2, I get -2. So in this case, my A1, my initial value is 1, but since my A2 is -2, that means my rate becomes -2 over 1, which is -2. And because the absolute value of -2 is greater than 1, the sum of this does not exist. Another way you can say it is it goes to infinity. We can't actually measure it because it's more than we can measure. All right, so I want you guys to try the 3 checkpoint problems at the top of the next page. And again, pay special attention to R. Okay, is the absolute value of the common ratio larger than 1 or less than 1? Because if it's less than 1, you can do it. If it's larger than 1, you can't. Try the first 3 checkpoints on the next page, and we'll go from there. All right, taking a look here, a sub 1 is equal to 5, but that's irrelevant because the common ratio is 9/7, which is greater than 1. The absolute value that's greater than 1, so the sum doesn't exist. We cannot quantify it within this set of numbers. Okay? In this case, a sub 1 is equal to 9. In this case, r is equal to 5/6. And since the absolute value of 5/6 is less than 1, then we can say that the summation of this series becomes 9 over 1 minus 5/6. Okay? Well, that's 9 over, and then 1 take away 5/6 is 1/6. 9 divided by 1/6 is the same thing as 9 times 6 over 1, which is 54. So that says if I added up all the numbers to infinity of this series, of this sequence right here, added up all those terms, eventually they would add up to the number 54. All right? In the next example, I would take 10/3 divided by 6, because again, I want to go this one divided by this one. All right, 10/3 divided by 6 ends up being the same thing as 10/3 times 1 over 6, which becomes 6 and 10 are both even. That goes in there 5 times and 3 times. So I get 5 over 9. All right, so does it make sense that if I multiply 10/3 times 5/9, I'm going to get 50/27? Well, absolutely it does. Because if I multiply this by 10/3, I'm going to get 50 over 27, exactly the next term, and then multiply again by 5/9, and I get 250 over 243, and so on and so forth. So my r is 5/9. My a is 6, and so the summation of this, again, 5/9, the absolute value of 5/9 is less than 1. Okay, 5 over 9 is smaller than 1. So the summation then becomes a sub 1, which is 6, over 1 take away 5/9. Now 1 take away 5/9 is 4/9. This is 6 divided by 4/9, which is the same thing as 6 times 9/4. And 6 times 9/4, 4 and 6 are both even. That goes in there 2 times and 3 times. I end up with 27 over 2, or another way to say that is 13.5. So those numbers are going to work towards 13.5 as I go out to infinity. All right? All right, so let's use an infinite series as a model. Take a look at a real life story problem here. Okay? It says, on some swing, a person's given a push on a swing. Their first swing, the person travels a distance of 4 feet. Don't worry about how that distance is measured, but the person travels a distance of 4 feet. Each successive swing, the person is going to travel 75% of the distance of the previous swing, assuming that they don't kick their legs and lean back and all that kind of stuff. You guys know how to swing, right? Okay, so the total distance they're going to travel is going to be the summation of all the terms, or if I start at 4, and then I get 75% of 4, and then I get 75% of 4 squared, because again, we're going to take 75% of the previous number, and we're going to take 75% of the next number, and so on and so forth. So basically, in this case, my r is equal to 0.75, and since that value is less than 1, that means that we can calculate this total series. All right? Now, this says that we swing for infinity. We never stop swinging. Okay, which is, as you guys know, is a little bit of a misnomer. But if we add up all the terms of this series, we get the initial value, which is 4 feet, divided by 1 minus 0.75. Well, as you guys know, 1 minus 0.75 is 0.25, so you get 4 divided by 0.25. Okay, and 4 divided by 0.25, if you want to use your calculator or some common sense there, remember this is the same thing as a quarter, so you can multiply by the reciprocal and you get 16. So it says the person will travel a total of 16 feet. So if we start at, our first path is 4 feet, and then we do 75% of that every time, eventually we can say that we traveled a distance of 16 feet. Try another one here. Let's try the example here in the checkpoint down below. All right, so now we know that our a sub 1 is equal to 3, or our initial distance is 3. All right, and so each successive term, the summation then, or the total distance that we travel, I'll just put d or s, okay, the summation or the total distance that we travel becomes the 3 feet plus 75%, 75% of the 3 feet plus 75% of that, so 0.75 squared, so we multiply by another 0.75, and so on and so forth. So it looks like then that my common ratio is 0.75, my initial value is 3, so 3 minus 0.75, 3 over 1 minus 0.75, so this becomes 3 divided by a quarter, which is the same thing as 3 times 4, or 12 feet. So the person would travel a total of 12 feet. Now, this is a really cool application of this. You may or may not be excited about this, but this is a really cool application of how you can use that to write a repeating decimal as a fraction. All right? So I want to write 0.474747, et cetera, et cetera, et cetera, as a repeating fraction. Right now it's a repeating decimal. I want to write it as fraction in lowest terms. All right. So the first term becomes 47 to the point times 0.01. And then we're going to multiply the next by another 0.01 because we want the next, this would give me the hundredths, and then we would have to get to the 10,000ths place, so another 2 zeros, so 0.01 squared, and then another, so this would now again be 0.01. Again, 2 decimal places here is going to get me 2 numbers with the 0.47. So it's 47 times 0.01, 47 times 0.01 squared, 47 times 0.01 to the third, and that's just going to give me the 4 and the 7 here. The next 4 and the 7 would come from 47 times 0.01 to the fourth, and so on and so forth, right? So my common ratio is 0.01. My initial value, my a sub 1, is this first term, which is 47 times 0.01, and that becomes 0.47 over 1 minus 0.01, which is my common ratio. Now 1 minus 0.01 becomes 0.99, and so I have 0.47 over 0.49, and if I multiply both top and bottom by 100, I get 47 out of 99. Okay, so repeating decimal 47, 0.47, 47, 47, so on and so forth, is the same thing as 47 out of 99. All right? 2 checkpoint problems down below. You guys try them, and then we'll finish up with lesson 12.4. All right, so the summation here, okay, the summation here becomes this number, 0.88888888. Okay, so we're taking the number 8, and we're going to multiply by 0.1, and then we're going to add that to the next term, which is the number 8, 0.1, well, this is really 0.01, or 1/10 squared, plus 8 times 0.1 to the third, and so 0.8 times 0.1 is going to give me the 8 in the tenths place. 8 times 0.1 squared is going to be tenths times tenths, or hundredths, so that's going to give me the number here. And then 8 times 0.1 to the third is going to give me the next 8, and you can probably imagine that the next one is going to come from 0.1 to the fourth. So my common ratio is 0.1. My initial value is 8 times 0.1. A sub 1 becomes 0.8. All right? And so if I want to write 0.8 as a fraction now, this becomes the initial value of 0.8 divided by 1 minus the rate, the common ratio, which is 0.1. Well, 0.8 divided by 0.9 is the same thing as 8 over 9. So that's 8/9. Okay, let's try another one. Okay, this is 0.63. So 63 times 0.01 plus 63 times 0.01 squared plus 63 times 0.01 to the third. And again, this 63 times 0.01 is going to give me the first 63. 0.01 squared gives me the next 63. 63 times 0.01 to the third gives me the next 63, and so on and so forth. Okay, so my R is 0.01. My initial term, my first term, becomes 63 times 0.01, which becomes 0.63. All right? And so this is 0.63 over 1 minus 0.01. Well, as you can imagine, the bottom is 0.99. On top, we have 0.63. Okay, multiply both of these by 100, and you get 63 over 99. Those numbers are both divisible by 9. 9 goes into 63 7 times. 9 goes into 99 11 times. And so 7 over 11, 7/11 is the same thing as 0.63 repeating. So that concludes your lesson on 12.4.